Singapore is running out of space. Space to develop and prosper.
There are more developments now. It's harder to find land.
Now, the little red dot is being re-engineered for the 21st century.
Nobody has done it before. This is the only job that allows you to work on a smart city project in Singapore.
We are going from about 350 megawatts of solar to 2 gigawatts of solar, and that's a huge jump.
New megaprojects using state-of-the-art technologies will harness the power of the sun.
It's a kind of new for Singapore to have solar panels on water.
Automate its ports.
I can't imagine. We will be developing a 60-plus berth.
And dig deep.
I did not believe the space-saving part until I saw it with my own eyes.
This is what engineering is all about.
All designed to find more space and allow Singapore to flourish. This is a journey into Singapore's Tomorrow City. It's a critical moment for one of Singapore's new megaprojects. One of the biggest machines on Earth is being delivered to a site in the heart of Singapore.
Slowly wire.
A tunnel boring machine, or TBM.
Today we are lifting all the main bodies for the TBM, just unloading at the site. We do this at night because the oversized cargo is only allowed to transport after 9:30 p.m.
The TBM is so big that all 6 parts have to be delivered one at a time. In Singapore, space is a luxury, both on the surface and at its only landfill at Palau Semakau, which is reaching full capacity. To create more space, one project is going underground to revolutionize waste disposal and water management. The Deep Tunnel Sewerage System, or DTSS, is one of Singapore's biggest underground projects at about $7 billion. This is the second phase, where 19 TBMs will carve out hundreds of kilometers of tunnels underground that will take wastewater across the island to different reclamation plants. To maximize space, the DTSS system will be dug deeper than any existing road and rail network, at depths between 35 to 55 meters. This is one of 50 shafts, the entry into the underworld, a gaping 10-meter wide hole known as Shaft M. It's nearly 50 meters deep. The work site at Shaft M is crammed with construction equipment, and lifting supervisor Johnson and his team must now find space for these 6 massive parts.
Okay, swing stop, stop. Slowly wire down. The space constraint is the biggest challenge for us today. $220 AM now. Going to shift the front body lower, 2 meters inwards. Then we're going to prep the cutter head unloading area with the timbers. It's the heaviest and it's the most delicate as well.
Once all the sections of the TBM are delivered and unloaded, they must be lowered one by one into Shaft M and then reassembled underground. The most important section of the entire TBM is the cutter head. The cutter head has a diameter of 7.5 meters and comprises of dozens of heavy-duty cutting discs that chew away at rock at a rate of approximately 3 meters every hour. Behind the cutter head comes the power source. The TBM is multi-purpose. As the cutter head bites away, this section erects the walls of the tunnel, which are made from these concrete rings. The cutter head generates huge quantities of waste or slurry, and this section of the TBM is its waste disposal system. To drive the TBM forward, thrust cylinders push against the newly built tunnel rings with a force great enough to shift an elephant. The cutter head arrives at the site.
All right, a little bit, swing right.
The engineers take special care unloading this spaceship-like equipment.
Okay, swing stop, swing stop. Boom up. Boom up. Okay, boom up, stop.
The cutter blades are precision engineered. The team positions wooden blocks underneath to prevent any damage to the blades.
Slowly swing to your left.
By the time the engineers complete the unloading, dawn is breaking.
Job well done, guys. Good job. Good job.
It will take another 6 weeks of preparation before the TBM sections are ready to be assembled in the tunnel below Shaft M. The deep tunnel sewerage system is not scheduled for completion until 2025. It is being built to last for at least a century. And so, engineers will inspect every detail of work during construction to make sure nothing is overlooked. One of the engineers on the inspection team is Wu Lai Lin.
So what are they doing in the shaft now?
Today exercise.
I've been doing DTSS since DTSS 1, which was completed in 2008. So yes, we have been talking about the Deep Tunnel Sewerage System, or DTSS, for many, many years.
By the time the DTSS is completed, it will free up 300 hectares of land above ground, more than half of which is currently being taken up by pumping stations and reclamation plants. The 19 giant TBMs still have 100 kilometers of tunnels to construct. DTSS-2 follows the heavily used Ayar Raja Expressway. To get all the TBMs working away below ground, 50 vertical shafts must be sunk along the route of the expressway, without disrupting traffic.
So the first thing we do is site the launch shafts, sink the launch shafts, and then we would launch the TBMs from these shafts. Then the TBMs will tunnel along happily, hopefully, until they reach the retrieval shaft, which is where we take out the machines.
Siting shafts along the Ayar Raja Expressway is a challenge.
Space is definitely one of the challenges. Can we find space on the surface to site our shafts? Or more importantly, to site a shaft big enough where we can actually launch our tunnel boring machines. There are more developments now. It's harder to find land for your shafts and things like that.
At Lower Delta Road, a new piece of machinery is changing the way shafts are being constructed and saving space at the same time. It's called the Vertical Shaft Sinking Machine, or VSM.
I did not believe the space-saving part until I saw it with my own eyes. It enables the construction of a shaft without the need for men to be inside the shaft excavating away. You can actually use it in very tight places, very close to existing buildings.
Site engineer Guo Hao is here to check the progress. One shaft has already been constructed and another is underway.
So this shaft is approximately 10 meters wide in diameter and is approximately 50 meters deep. How's the site progress?
Everything goes well. Today we are going to finish the calibration of the VSM. So after that, we'll fill water.
Okay.
Start excavation.
VSM that we are currently using is the only VSM machine in Asia, as it's a relatively new concept compared to a traditional excavation method.
The system works like this. First, a narrow shaft is excavated to a depth of about 10 meters. Then it's lined with prefabricated concrete rings. Now, the shaft is ready for the VSM. which has a telescopic arm with a road head that can swivel around to dig deep. The engineers must carefully calibrate the robot arm before they set it to work.
So how a VSM works is that there's a cutter drum. So this cutter drum will move towards the shaft in and out as the arms will turn. Is it okay?
Length is 80.
The VSM is doing vertically what the TBM or tunnel boring machine is doing horizontally underground. As soon as the cutter drum excavates a complete circle of 100 millimeters, both shaft and cutter drum will move downwards. It takes at least 10 hours to dig 1 meter. As the ground sinks, engineers will insert concrete rings that form the shaft wall.
Okay, stop. Checking.
Okay, please measure the length.
Okay, done ready. That's all. Thank you very much.
Okay.
This is the last time engineers can enter the shaft. Once the telescopic arm is calibrated, the opening will be filled with water for the machine to begin the excavation work.
This is what engineering is all about. So where we come up with solutions to reduce the risk of workers and to actually improve the efficiency of excavation.
The VSM system lets the tunnelers do their job in cramped urban sites, like the one at Lower Delta Road on the expressway. But underground, the engineers will soon confront the biggest challenge of all, Singapore's subterranean geology. Singapore's planners are spending billions of dollars to build a new waste disposal system, the DTSS. Huge tunnel boring machines are at work deep beneath our city. Down here, the biggest problem for the engineers is the geology, the hidden world beneath our feet.
So between where I am standing now and perhaps just behind the camera, the ground conditions can differ greatly. So it's difficult for a tunnel boring machine to be catering to different types of ground conditions that are changing so rapidly.
Adam Switzer is a geologist at Earth Observatory of Singapore. He has spent many years studying the geology of Singapore and understands its challenges for tunnelers. Tanjong Rimau is one of the few places locally where the hidden world beneath is exposed. These rocks were laid down millions of years ago and over time have been twisted and folded by the movements of the Earth's crust.
Much of the geology of Western Singapore is like this. Lots of different rock types, very closely placed together and very complicated in terms of folding and small faulting, which means that in engineering, that adds a lot of complexity. So if you look here, the rocks change a lot over a very short distance. And you've got your engineering system running in a way that drill through sandstone, and all of a sudden you come into a muddy shale like this unit here, or you run into a bed that's full of big boulders, which we have in Singapore as well, then your engineering is going to run into problems.
And that's what's happening in Shaft X1, located by the Benoi flyover along the Ayer Rajah Expressway. Irregular readings from the instruments on the tunnel boring machine, or TBM, have put a stop to tunneling works.
Well, before we start our works, of course, there's a whole series of site investigations done, boreholes are sunk and all that, but you can only sink that many boreholes that close apart. So you have some idea of the ground conditions we are encountering. So between two boreholes, you could draw a line that shows you where the rock head is, but in reality, it could go this way, you see.
The exploratory boreholes were sunk here before the tunneling started. Despite that, ground conditions still proved tough for the cutter head to tunnel through.
Can you switch to the normal screen?
Yes.
We are at
2.9 bar.
Yes.
For engineer Christian Schilling, one of the most important tasks is maintaining the cutter head. As the TBM inches forward, the cutter blades are constantly worn out, and the huge machine must be stopped periodically for maintenance. And in subterranean Singapore, it's a tricky operation.
So this is an example of a mixed phase, right?
Yes.
Yeah.
Mix of rock and soil. And these are the rock.
Yeah.
And these are the soil.
Ah,
These
okay.
can break.
I can feel that this is like soil. It's much softer, and then the one you actually have here is actually quite hard.
Oh, true.
Yeah.
To understand the ground conditions, engineers examine samples of the rocks excavated by the TBM and confirm that the rock face they've been tunneling through is made up of a mix of hard and soft materials.
At the moment, we have stopped the TBM for a cutter head intervention.
To carry out a cutter head intervention, or CHI, a team of engineers enters the space at the front of the TBM. But Schilling has to choose the right moment, when the ground ahead is stable and less likely to collapse on the workers.
The geology, let's call it interesting. Up to now, on these over 500 meters, we had mainly soft rock. Now we are, since about 200 meters, in a soft geology. It's mainly clay. It's never a good time, because of course we want to continue tunneling. But we have to.
That time we need to check what's the level of the rock and what's the level of the soil, and based on that we prepare this face mapping. Okay?
The TBM is tunneling 50 meters below sea level, and the air pressure down here is much higher than at the surface. For the team, it will be like diving underwater, and like divers, they will need to acclimatize to the pressure.
This particular one, we have finished changing our disc cutters. That was 10 pieces this time. And now we still have some scrapers to change, the soft ground tools. And then tomorrow we should be on the way again.
The TBM engineers can only plan ahead if they have a good idea of the kinds of rock and soil that the TBM must cut through. As they push forward underground, geologist Adam Switzer and his colleagues continue to map out Singapore's subterranean world. Today, they've come to the north to investigate the mysterious Sembawang Springs. It's an area famous for its 70 degrees Celsius water source, and this.
We place the eggs here, and we leave it about 1 hour. Maybe the thing will be boiled.
Our eggs were a bit runny. We put them 20 minutes under the hot tap, but they were good. It was
tasty, yeah, and it was fun to be able to cook them outside and in the water.
Yeah.
The Sembawang hot springs do more than cook runny eggs. They provide vital clues to Singapore's subterranean geology. Singapore isn't known for earthquakes and volcanoes, so the puzzle is, where is all this heat coming from?
It's quite rare for a hot spring to occur in a setting like this. You need hot rock source. It needs to be shallow enough that it still gets to the surface with some heat capacity. And the water's coming out here at about 70 degrees. It's enough to cook eggs. And so, you know, that means that heat surface must be reasonably proximal.
At the Earth Observatory of Singapore, geophysicists are using state-of-the-art technology to solve the mystery of the springs and to look deep under the surface of the island. The hot springs are evidence of an active fault line located somewhere deep below. A fault is a fracture in the Earth's crust, and here it heats groundwater that is conveyed to the surface at Sembawang to steam up those springs. Faults can also become active and cause earthquakes. But where exactly is this fault? And could it pose a danger for the DTSS tunnelers?
So this kind of instrument is actually our ears. And the earthquakes or any other kind of seismic source are like our hands patting on the watermelon. So when this energy penetrating through the earth, it carries the information about the underground structure.
The team positions seismometers at locations all over Singapore to record the data.
I'd adjust the position a bit.
Yeah, it's ready.
Yeah, it's working now.
Yeah.
You can just take it off and then sit.
Over a period of 5 weeks, the seismometers record vibrations from road traffic, construction, and far-off seismic events. The result is a digital portrait of underground Singapore, which they hope will pinpoint the location of any dangerous fault line.
This is actually in the very high frequency.
So this kind of map tells us what kind of rock that is under the ground. So these numbers are representing the speed of the shear wave that is traveling within the earth.
We can work out where this fault line is, which is separating the granites in the middle and the Jurong Formation sediments in the west. And that's really important when there's construction work underground.
The team will need more time to install additional sensors to figure out possible problems lying in wait for the tunnelers. With expanding built-up areas and new mega projects like the DTSS, the information will provide insights and help avert disasters, like the Nickel Highway incident in 2004. On April 20th, 2004, steel supports over the Circle Line MRT tunnel below the 6-lane-wide Nickel Highway collapsed.
The disaster triggers a blackout and plunges traffic into chaos.
Construction work for the Circle Line had to be stopped, and the highway closed for 7 months for repairs. The lives of 4 men lost. This catastrophe still serves as a haunting reminder today. Huge megaprojects like the DTSS are built to last into the next century. The tunnel is 22nd century technology, but the project depends on one of the oldest of all building materials, concrete. And one of the most critical ingredients in that is running out. There is no limit to Singapore's ambition to build the city of tomorrow and to free up space for the future. To achieve this, the new DTSS, or the Deep Tunnel Sewerage System, is burrowing deep beneath Singapore to create a network of tunnels that will revolutionize waste disposal and water management. All kinds of waste will be treated, reducing the amount of throwaway rubbish and generating energy in the process. The DTSS will redefine recycling for the future and take the pressure off Singapore's only landfill site at Palau Semakau, which is reaching full capacity. But solving the problem of waste on such a scale creates another. Construction projects like the DTSS are hungry for concrete. And this demand is escalating the need for a key ingredient, sand. And sand is in short supply. At the Nanyang Environment and Water Research Institute, researcher Zhen Hui thinks he has found a solution.
Basically, concrete is made of cement, and then fine aggregates such as sand, and then also coarse aggregates such as pebble or bigger rocks.
It's the binding between cement and aggregates like sand that makes it strong enough to take high compressive loads, making concrete the perfect raw material for megaprojects like the DTSS.
The sand is mostly used in construction are the river sand. The world uses almost 50 billion tons of sand every year. We don't have enough sand.
Zhen Hui believes he has the answer to the sand shortage: waste. He is convinced that waste can be the new sand and a solution to better quality concrete.
Our aim is to improve the quality of a concrete. We have this project with NEA. We have this waste to energy research facility. We use a very high temperature gasification to convert waste into very stable gasification slag. We call it new sand.
The key to the process is heat. High temperatures of 1600 degrees Celsius to be exact. This produces gas that can be used for power generation and the rather unattractively named slag or new sand. In this process, very little is wasted.
This new sand is made from pure waste. We are trying to use it to replace sand at higher ratio. This slag is a very new material, and we do not know a lot of the properties about this. And then currently our research is still doing the characterization and then to understand fully this material.
The big question is, how does new sand compare with river sand?
We can see that the river sand consists of a lot of very fine particles with occasional large particles. All the sand particles are more of rounded because of the natural erosion along the rivers.
The consistent and rounded size of river sand particles help them to bind easily with cement.
So for our new sand, the slag, gasification slag, we can see very distinct rod-like structure, which are known as glass fiber, and also very angular particle.
Zhen Hui is carrying out a test to compare new sand with river sand samples.
So we're doing a 50% replacement ratio. So the design mix will be 4 kg of cement, and then we do 2 kg of sand and 2 kg of slag. So we'll be putting in the cement and the fine aggregate into the mixer, and then we will start the mixing process.
His sample will now undergo a compressive test to see how much load or weight they can withstand before cracking. He starts with the typical concrete cube.
So in the lab setting, we test the amount of load it can take through the compression machine. We keep applying higher and higher compressive strength onto the concrete and then see the maximum load it can take before it cracks or before it fails. So we can see that as the strength increases, the deformation increases very rapidly.
Next, Zhen Hui tests the new sand concrete. The higher the number, the more load or weight the concrete cube can take. The number to beat is 82.4.
In our new sand concrete, you can see that as the strength increases, in the initial stage, there is very little deformation.
And the winner is new sand. The superior strength of new sand is all to do with these rod-like structures which bond with the cement. With the theory proven, this new sand concrete will soon be ready to be tested in reality. At Portsdown Road, engineers have reached a critical stage in the DTSS project. Preparations at Shaft M have been completed, and it's time to lower the 6 different parts of one of the largest TBMs, also known as tunnel boring machines, into the completed shaft. It's a very tight squeeze. The entire process will take at least 2 weeks.
Okay, so means we lower down the erector after 1 p.m. Correct?
Yes.
Yeah. So one of the milestones is to complete the assembly of the TBM so that we can proceed the next step, which is the mining work.
Below ground, engineers begin connecting the different sections of the TBM. The completed parts are pushed into a pre-excavated opening to make space for the next piece. Then comes the second stage. These gantries will house the control cabin, electrical supplies, and rail tracks to transport tunnel segments. As soon as the TBM has chewed its way about 100 meters into the rock, the remaining gantries will be lowered into the shaft. When completed, the machine will be 130 meters long, the length of 10 buses.
This is one of the biggest TBMs so far in Singapore. That's why it needed to be segmented in a bottom part and a top part. So to make sure the alignment is correct, it is all properly sealed. During the assembly, we need to pay attention that all these seals are staying in place.
Senior project manager Uli is another tunneling veteran. Today, he has come to the Portsdown Road site to make sure the assembly is proceeding according to plan. It doesn't take long for eagle-eyed Uli to discover that there's something wrong.
I've been down to the shaft and have inspected the tightening of the bolts and the status, and I've reported to the main contractor. If the bolts are not tightened, we cannot proceed with the cutting wheel installation. The TBM is applying support pressure at all time to the tunnel face from stopping it from collapsing. So if the bolts are not tightened properly, there will be a leak through the shield segment.
The only solution is to work through the night to tighten the bolts, all 280 of them. The next morning, Uli returns to the site to find out if the problem has been resolved.
Hi Uli,
what's the situation?
Yeah, we are ready. So now we are coiling up all the wire into the drum. Yeah, we are make sure all the wires will be quite nicely in the drum. Okay. Then we'll be ready to hook up.
When the cutting wheel is just 1 meter above the cradle, we'll slide the front body forward. So this is to prevent damage to the rotary coupling.
This is the cutting wheel, the biggest and heaviest section of the TBM. Its size and weight explain why Uli is so cautious.
We shifted the TBM backwards so that there is a big enough gap to fix the cutting wheel in front of the TBM. Nevertheless, it's getting very, very tight.
Now, the tricky process of lowering the cutting wheel 50 meters down to the shaft bottom can begin. And it's a very tight fit.
Space is 500. Yeah, it's very tight. We have to make sure that it's not swinging and touching anywhere. Yeah.
If any part of the $1 million TBM is damaged, the consequences in terms of repair costs and delays would be catastrophic. As the operation begins, it's all hands on deck. There's just a 5-centimeter gap between the cutting wheel and the shaft wall.
The rotary coupling was actually colliding with a shield on top. But we managed to make up enough space to fit the cutting wheel down.
After 2 hours, the TBM section reaches the bottom of the shaft safely, 1 day late. The engineers are relieved. The hardest part is over, and the cutting wheel can now be attached to the front body.
So far the progress okay. Of course, plan schedule will be delayed 1 day.
but we sure can catch up.
Going underground is an important solution to Singapore's diminishing land space. A new urban scheme at Punggol in northeast Singapore is going to show that putting transport links underground is a way to return city streets to the people that use them. Space is a luxury in Singapore. To create more room on the surface, projects are going underground. But city planners have come up with another way to tackle the problem. And it's simple. Plan cities in advance to maximize space. That's the concept behind the smart city. And the first in Singapore is Punggol, where a new district has been planned from scratch. Led by Gilbert Cher, the team has designed a digital district which is targeted for completion in 2024. It comprises a business park and a university campus, an environment where business professionals, academics, students and their families can call home.
So, Punggol Digital District, together with a few other districts around Singapore, are one of the ideas of decentralization.
To maximize space for people, the planners made a crucial decision. All transport links are being built underground, from the new MRT connector to huge car parks, leaving the ground level free for pedestrians and cyclists.
I can tell you where's my favorite angle of the model. When you look at this model, it's actually right down here, looking towards the west. You see the main street, which is really Campus Boulevard. You can actually see how the business park, the SIT campus are really stitched together into one very cohesive whole. So this is the whole concept of space swap, where we are looking to have the deeper academia industry collaboration.
And that's not all.
Room service.
At the beating heart of the smart district in Punggol is a new software. It's being developed by James Tan and his team. It's called the Open Digital Platform. It allows them to test out smart systems and real-world scenarios virtually.
Hey, guys, can you zoom out? Can see the details of the construction progress? Yeah. This is what we call a digital twin. Why we do this is because we are able to have a good spatial view of what's happening in the real world, especially when all this real-time sensor data comes in. Nobody has done it before. This is the only job that allows you to work on a smart city project in Singapore.
The idea behind the Open Digital Platform is to integrate smart systems with everyday life.
At some point, we will need to integrate with the PDD meeting room booking system. If no one is using the room, we should do a reality check that the meeting room is 0. At this view, I don't have one shot, like where's the one that is overcrowding. So what we hope to achieve is to derive better efficiency through energy savings and of course manpower distribution. On the other hand, we want to make people's life easier. In fact, we were coining about the idea of giving people 27 hours instead of 24 hours because we think they can save 3 hours out of every day through less waiting time, faster moving into your office, leaving the office, and so on.
While the digital team works out the smart services, 2 meters underground, another team is spearheading the physical construction of the Punggol Digital District.
Hey, Chai.
Yeah.
Any idea on the concourse level or the shop drawing status?
In preparation for the tunneling works that will connect the digital district to the transport network.
Are we reaching B1 already?
So this one we are target to complete 1 month after the MRT roof completed. But this is a temporary slab. So we are following closely with this construction sequence.
Project engineer Wing Ze has worked on this from the start since 2017.
We are working towards the Tunnel Breakthrough event, which is a big milestone for GTC and LTA collaboration. We are doing okay, but of course all the construction projects is affected by COVID, but we are catching up.
And she is in charge of preparing the basement works.
So now the machine is behind. How far away?
Still outside.
Okay.
The giant TBM, or tunnel boring machine that has eaten through over 700 meters of soil from the existing Northeast MRT line, is about to break through, right here.
One of the key challenges is that we are going under a live LRT pier and a viaduct. So obviously we tend to get a little bit more cautious. We're going very close, make sure that we don't affect the LRT structure.
When a TBM tunnels close to critical areas underground, it's high alert for the whole team across the project. These critical points are known as influence zones.
The challenge is to actually monitor the instruments in the TBM carefully so that we can not over-excavate to lead to sinkholes. The results will be very disastrous.
At Benoi Flyover, the team is on high alert. 2 tunnel boring machines are tunneling in close proximity to the overpass. The 2 massive TBMs working together may destabilize the flyover, so the engineers continuously monitor the structure for any signs of weaknesses.
So monitoring is extremely important. All our monitoring data is gathered on this online platform so that you can access it at any time. So let's say you're getting readings that give you maybe excessive settlement, we will be alerted.
Please take note that our tunnel is approaching the expressway. Any anomalies or significant changes, please do highlight to your engineer. We are here below the Benoi flyover where it is considered one of the critical structure for the project. So along this area, we have installed 3 sets of instruments for each of the TBMs. So this will be monitored during the mining works.
The risk is that as the TBMs move forward underground, the soil above the tunnels compacts, causing a depression to form at the surface and, in the worst-case scenario, develop into a sinkhole. In densely packed Singapore, this would be catastrophic.
This is a big area, and in Singapore, most of our areas are quite congested. So you are either underneath a road, if not, you are underneath some kind of services and everything.
These instruments are part of a vital early warning system if anything is amiss. Readings from the sensors are closely monitored. With his decade of experience, Christian Schilling keeps a close eye on the progress.
The TBM is moving constantly forward when we are tunneling. Everything okay here?
Okay, boss.
Good. They are.
So far, no warnings from the sensors above ground.
So basically, we see from the survey system the actual position of the TBM. We have our navigation screen that shows us where we are currently, how far we are off the alignment.
Finally, the TBMs pass the critical risk zone, and the next tunnel ring can be built. Back at Pongol, after tunneling past the vital LRT pillars, the last few centimeters are about to give way, signaling the end of the MRT tunnel and the machine's journey. Everyone gathers for this momentous event.
Fantastic breakthrough. Very well coordinated and planned. All thanks to you. Yeah. Okay.
Such a good job.
It's a job well done for the team at Pongol.
The moment you see the crack, you know that it's coming next. And within 2 minutes, the whole wall collapsed. I think you can hear all the cheering sound for everybody. That's how we live from the entire team, JTC and LTA, that finally we do it, we have done it.
DTSS-2 still has 4 years before it will be completed. As Singapore reaches for the sky, building gleaming towers of glass and steel, deep below, 19 giant machines continue to excavate a network of tunnels stretching 100 kilometers. This will transform how Singapore manages water and waste, propelling the state into the next century and building a new pillar of Singapore's tomorrow city.